Welcome to the Sound on Sound recording and mixing podcast channel. My name is Mark Mynett, and in this episode we are looking at the mix stage of the production process. As part of the mix process, we'll be looking at balance and stereo width, we'll be looking at compression and signal chain order along the way, obviously looking at EQ. We'll then be looking at effects processing and automation, and we'll briefly touch on master bus processing. However, it's important to firstly state that although mixing is usually associated with creative processes, there's usually a significant level of technical tasks. And those technical tasks typically involve potential performance edits and or reamping, setting up mix groups, polarity summation, waveform edits, and all of these technical tasks, it's better to take care of these first before moving on to the creative stages, and it prevents those creative stages getting interrupted. So what we'll do, we'll quickly consider these technical tasks that tend to be required for most mix projects, and then we'll move on to more of the creative processes. Firstly then, take care of any performance edits, including quantization, potentially with your drums, and any bass or guitar reamping. Take care of those first. Don't break up your mix process by starting mixing the drums, for example, then stopping to reamp your bass and or guitar. From here, I recommend setting up your mix groups, aka auxes or sums. In essence, a way to combine a number of channels into a single audio path. For example, if you've got 4 electric guitars, sending them to a stereo mix group gives you the ability to control all of them processing and or level wise. From here, I highly recommend taking care of polarity summation with your drums. This is a part of the mix process that is absolutely critical, and so many novice mix engineers miss this step out, which tends to result in a series of frequency cuts, usually most significant in the low end, that progressively lead to a given drum sound being hollowed out. Worth mentioning here is that I'm using the term polarity summation, not phase. Phase actually relates to time of arrival differences, potentially of a single mic recording the sound source as well as reflections off the surrounding acoustic space, or multiple mics, for example, a snare top and an overhead mic capturing a snare drum at different times. That's time of arrival differences. This is very different than polarity. Inverting the polarity of a signal means reversing its amplitude, so the positive portions of the wave become negative and the negative components become positive, which, as you can see, is neither time nor frequency dependent. So what we're doing here is trying to find the combination of polarity settings that provides the fullest low frequency reinforcement across all of the drum components. And because unconstructive polarity settings tend to reveal themselves most notably in the low end, adding low frequencies to one or both sounds, for example using a low shelf on both of the sounds that you're looking at polarity settings for, perhaps with a broad extensive shelf, can help clarify your polarity setting decisions. Starting with a single overhead track in solo, we're going to use this as your reference anchor, to which you're going to introduce a further overhead track at equal perceived loudness, and then toggle the polarity on this track to establish which setting provides the most low frequencies, which is usually accompanied by additional level. If you don't hear any difference between the polarity setting, you can just leave it as was. But as I've already mentioned, if you want to add low frequencies to the reference anchor track, as well as the further track that you're introducing, that usually helps reveal the most constructive polarity setting. Then continue looking at the optimum polarity settings for your other cymbal focused microphones, particularly your hats and ride. Once you've established an optimum combination of settings with the cymbals, hats and ride, the drum shell spot mics can be considered. As the kick and snare are likely to have been multi-mic'd, possibly the toms as well, you first need to establish the optimum polarity combination at a component level. So if you've double mic'd your kick drum, for example, I recommend taking care of finding the optimum polarity settings between the two kick microphones before considering them within the overhead mics. And in this instance, you're just using the same technique. You're just using one of the kick tracks as an anchor track, a reference anchor, introducing the other one and experimenting with which polarity setting reveals the most low frequency content, which is usually accompanied by additional level. From here, you can use your mix group, your kick drum mix group, to experiment with inverting the polarity to see which polarity setting provides the most low frequency reinforcement with the overhead mics. In this instance, it's recommended that you kind of bury the kick drum into the overhead track to reveal these polarity settings. If the kick drum's really loud, it'll completely overpower the influence of the kick drum in the overhead mics. Carry out the same procedure on your snare track and your tom tracks, and from here, the only other signals to consider will be your room mics, where you're using the same principle as previous. However, some producers like to experiment with phase alignment. They like to take the room mic source and, for example, phase align the way that the room microphones captures the snare with the snare spot mic. There is some software like Sound Radix's Auto Align that does this for you, and also Sound Radix Auto Align can give you the optimum polarity setting as well. But it's always good to know the manual approach for polarity summation, which you should also apply to your bass guitar, for example, between your DI and your cab or amp sim track. And likewise, it's good practice if you've double mic'd your guitar takes to check polarity summation as well. Moving onwards, last couple of technical considerations before we move on to the creative processes is firstly waveform edits. So removing unwanted hiss and noise, for example, on your guitar and bass tracks, and removing incidental noises, maybe headphone spill or other unwanted incidental noises. And potentially with your tom tracks, you will need to make a decision whether the spill captured on those tom tracks is going to contribute towards a greater sense of drum cohesion. And you need to make a decision that if you are going to attenuate that spill, are you going to use gates or potentially waveform edits? Now, what you can do is use limited range gating so that you set the range of the gate to maybe 12 dB, so it just attenuates the spill by 12 dB rather than 40 dB or 80 dB, again giving you that option for the spill to contribute towards a greater sense of cohesion. But if you are going for quite aggressive attenuation of that spill, I tend to find that it's preferable to use waveform edits to go through, remove the spill, use a very quick fade into the tom hit, then a longer fade out, matched to the sustain of the given drum. And what I tend to find is that once you've done the waveform edits, you don't need to revisit them. With gates, you will often keep going back. You know, you've got a floor tom that goes directly onto a ride and you want to kind of like pull that spill out quickly. It's much easier to do with waveform edits than automating gates for the same. What I don't recommend though is using waveform edits to attenuate kick or snare spill. If you are attenuating that spill, as I've mentioned earlier, you might want to use that spill as a contributing quality towards a more cohesive drum sound. But if you are attenuating the kick or snare spill, I recommend gating, and don't forget that you can apply limited range gating if you want the spill to contribute towards a more cohesive drum sound, but you don't want to leave it unchecked. You can set your range of your gate to 15, 20 dB, whatever you like, to attenuate that spill accordingly. From here, you can move on to multing, should you actually want to do that. This is the process of separating performance sections, usually with different dynamics or timbres onto different tracks. For example, if you had snare performance with very, very fast performance to a slower backbeat, it'll often make sense to copy the faster sections onto a separate track, which really helps reduce the amount of automation required to get the different performance subdivisions to work as you would want them to. And then lastly is just drum sample implementation. There's various methods to do this. Tab to transient within Pro Tools is very accurate but very time consuming. And then there's a whole host of software methods. But the method that I actually prefer is converting the drum hits to MIDI information. I use a plugin called Massey DRT for doing this, and then using a virtual instrument, in this instance Native Instruments Battery 4, which provides a really powerful level of control over different samples that get triggered and from different MIDI velocities. So then let's move now on to the creative mix processes. Starting off, let's just consider two fundamentally different approaches to starting the mix stage. One of which just involves setting up a very basic mix, but without any processing and just using pan positions and balance. This establishes the central mix challenges and should provide a broad framework of the processing tactics required. The second approach involves sort of starting from the beginning and sort of like going left to right across your desk or your DAW. So starting off perhaps with the kick drum, gating, compression, EQ, then building the snare into the equation, building up the rest of the drums before introducing the bass, etc. Here there's a little bit of a danger that you can spend a lot of time processing certain signals without being informed by how the other components of the mix impact that signal. So in other words, spending a long time EQing your snare drum without factoring in how the sound of the bass and the electric guitars will inform that. There's a third approach which kind of combines the two, which involves rough initial balance and pan positions, but with swiftly applied processing throughout. And again, this highlights the main challenges of the mix, but in this instance with enhanced context. Whichever of these three approaches you use, my recommendation is that any processing that's been applied through the tracking stage is removed and you actually start from the ground up. And again, don't forget those technical tasks that I've already talked about, especially polarity summation. It's one of the fastest ways of undoing a lot of mix work, is realizing that you haven't established your drum polarity summation settings halfway through the mix stage. One other consideration before you really get into the mix process is your master bus processing, specifically compression. My own experience is that I much prefer to have a mix compressor in the signal path right from the mix start, so that I'm mixing into that all the time and sort of like going back and retaining that nominal level of compression, usually 3 to 4 dB of gain reduction throughout the mix stage. It seems slightly counterintuitive to me to be into the mix stage and then later on you put the mix bus processor in there, meaning you're going to have to compensate for the way the collective instruments respond to the mix bus compressor. On the subject of which, I can recommend VCA compression, as it tends to be the cleanest. For example, the SSL G-Bus compressor or the API 2500 as being well suited to a mix bus compression role. And I recommend retaining 3 to 4 dB of gain reduction, starting off with a 10 millisecond attack time, maybe quickening that attack time up if you've got quite a fast mix. And then 2-to-1 ratio, especially with the G-Bus compressor, gives you quite a soft knee, which is beneficial for a mix bus compressor role. And make sure that you're returning to your mix bus compressor to ensure that you're retaining that nominal level of sort of 3 to 4 dB gain reduction. Moving on to our core processing tactics of compression and EQ. So let's just briefly consider signal chain order. There are no hard and fast rules here, and if it sounds right, it is right. But if you apply EQ before compression and you're adjusting those EQ parameters throughout the mix, this changes the signal level going into the compressor, meaning that you will often have to revisit your compression parameters, often your threshold. Additionally, you'll tend to find that additive EQ boosts tend to sound more focused post-compression. When they're placed before compression, the compressor almost tends to counteract these mix gestures. Nevertheless, in many instances, any corrective EQ gestures tend to be more effective before compression, because it prevents the compressor overreacting to these less desirable frequency ranges. So what you can see here is a general principle is that if it's fairly subtle EQ and compression moves, the signal chain order doesn't matter so much, it has minimal impact. Whereas if you've got significant corrective EQ moves, they tend to be better before compression. Likewise, if you've got significant boosts from an EQ unit, they tend to sound more focused post-compression. Once again though, if it sounds right, it is right, and if you're going against this general signal chain order principle and it's providing the right results, then that's absolutely fine. Let's stay with compression, which for audio purposes is a device that automatically modifies a signal's dynamic fluctuations. And whereas that's certainly the case, the real beauty of compression comes from its coloration capabilities and transient design, which are important considerations because you need to understand what you're doing with compression and why. That's the first thing, is why are you using compression? What are you trying to achieve? And is it signal stability, or is it coloration, or is it transient design? And from that perspective, choosing the right compressor topology for the task is really important. We've got 4 different types of compressor, namely VCA, which is an acronym for Voltage Controlled Amplifier, FET, which is Field Effect Transistor, Optical, and Valve Compression, or Tube for our US cousins, which is sometimes referred to as very new. Generally speaking, VCA compression tends to be the cleanest, so the least harmonic distortion and coloration, and VCA also tends to be the best all-rounder. So VCA compression is great with drums, but likewise great with almost any instrument. It's a great all-rounder. However, for certain processing tasks, such as room mics and also gaining very powerful control over vocal signals, FET compression is very favourable. FET compressors tend to have a lot of coloration capabilities, but they're also very, very fast compressors. So the quintessential FET compressor, which is the 1176, has an attack time that's within 1 millisecond. And don't forget that the attack and release controls are often considered to be the wrong way round. So we're setting the control fully clockwise is actually the fastest attack setting, and fully anti-clockwise is the slowest setting. But even at its slowest setting, an 1176 has an attack that is within 1 millisecond. So it's a very, very fast compressor, and again, it can provide a lot of harmonic coloration to a given signal. Optical compressors tend to exhibit the slowest response time. So a quintessential optical compressor is the LA2A, which is program dependent ballistic, so attack times and release times that depend on the program material it's applying gain reduction to, but it averages around 10 milliseconds. But importantly, these compressors don't have attack or release parameters, which means they're fairly redundant when it comes to transient design, but they can provide great coloration and great sort of RMS-based signal stability to vocals, and also very favourable for bass guitar. The last compressor topology is valve, aka tube / Very-mu, and they tend to be less compatible with transient design, similar to optical, but also highly effective at introducing musical colour and character to given signals. Again, they tend to be very favourable on bass and vocals and a whole range of other instruments, but you just need to be careful there that they're not well suited, as I say, to transient design. Before turning our attention to transient design with drums, let's briefly consider signal stability, which, if you listen to last month's Sound on Sound recording and mixing podcast, which was actually on recording vocals, you might recall that A favourable way of approaching your compression is to go with quite high threshold so that the loudest parts of the signal are still overshooting the threshold, but with a high ratio so that those parts of the signal overshooting the threshold are quite radically brought down. That's usually an effective approach for gaining more signal stability with the signal. But moving on to transient design, what we're going to do is firstly, we're going to over-exaggerate the likely levels of gain reduction that we're going to require. We're actually going to look at about 16 to 18 dB of gain reduction, which certainly for your spot mic sources tends to be excessive levels of gain reduction. But what we're going to do is just try and establish how adjusting the attack parameter allows the compressor to grab the transient of the signal. We're going to use a snare drum as a processing example here, but the principles of transient design here remain relevant to your other drum sources and indeed other instruments where you want to change the relationship between the attack, decay and the portions in between those components. Let's just listen to the snare drum without any compression. And now using the API 2500 compressor, which is a VCA compressor, you're going to hear the snare drum quite radically compressed with an attack setting of 0.03 milliseconds, which is very fast indeed, to 3 milliseconds, to 10 milliseconds, to 30 milliseconds. And listen to the way that the sustain is impacted, but also the transient, the punch element of the drum sound. As mentioned earlier, it's not always entirely clear, it's not as intuitive as with EQ, the changes that are taking place when you apply compression. So let's just listen to the fastest attack time directly to the slowest attack time from 0.03, very, very fast, to 30 milliseconds. And what you're hearing is the first snare hit, the one with the fastest attack setting, has really had its decay portion emphasised. The sustain of the snare is greater, and this is clearly because the transient, the punch information, has been reduced and the compressor releases to bring up the decay of the snare drum. Then directly contrasted with a 30 millisecond attack time where the transient element of the snare hit is largely allowed through. Important to note is that as soon as a signal overshoots the threshold, gain reduction starts immediately, but the attack setting is the period over which gain reduction is introduced. It's not a case of that if you've got a 10 millisecond or 30 millisecond attack time that the compressor waits for 10 or 30 milliseconds before applying the gain reduction. It's the period over which the gain reduction is introduced. But with a 30 millisecond attack time, the transient is largely allowed through without that much influence of gain reduction, and then the gain reduction is basically, it's attenuating the sustain, the decay of the drum. And if I wanted to even suppress that sustain decay portion even further, I'd go with a longer release setting. If I wanted a very emphasized transient and very little sustain, I'd go with a longer release. But that's what you're hearing there. But to my ears, both of those hits sound quite unnatural. The decay sounds overly emphasized with a 0 or close to 0 attack setting, and similarly the transient sounds overly emphasized with the 30 milliseconds. So I'd certainly be making a comparison between the 3 millisecond attack time and the 10 millisecond attack time, which sound like this. And hopefully you'll be hearing the relatively subtle difference, but a difference nonetheless between the 3 millisecond and the 10 millisecond attack time, allowing you within the context of your given production to make a decision as to which is the most appropriate setting from a transient design perspective. And after establishing this attack setting, you could either lengthen the release to suppress the decay portion, or quicken the release to allow the gain reduction to release, which emphasizes the decay a little bit further. It's just a case of analysing the results of your compression settings to establish what it's doing in the way that it rebalances the punch, the transient and the decay and the portions in between. And again, doing that within the context of the production. But don't forget, along the way, you're likely going to want to reduce those levels of gain reduction. You were listening to around 16, 18 dB of gain reduction there, which certainly tends to be way excessive for spot mics. But in any event, your snare, or indeed kick drum toms, whatever the component you're compressing is likely to sound like it's been hit harder, and with one of those semantic descriptors is more aggressive, and that's because it's been subject to coloration, and that's the real beauty of compression, which in simple terms equates to enhanced harmonic content and enhanced timbre. And just staying with this subject of coloration and enhanced harmonic content with the drums a little bit further, if there's one element of a drum recording that tends to be most subject to additional harmonic content and coloration, it's traditionally and typically it's the room mics. And from this perspective, we can sort of consider the room mics as the radical alter ego to the spot mics. What tends to happen with spot mics is that we gate and or waveform edit with the toms quite often to enable control, so that when we're turning the snare drum up and down, we're not turning the hats up and down at the same time, and gives us that control that when we're, for example, EQing the toms, what we're doing to make the toms sound really nice isn't negatively impacting the spill that compromises the drum sound. But of course, there's so many different approaches, and it's important to state that quite often spill captured on your kick, snare, sometimes your tom mics contributes to a more cohesive drum sound. But a typical approach of a lot of mix engineers is to enable that control throughout your spot mic, so the gating of the kick and the snare, gating of the toms, or indeed waveform edits, that's my preferred approach, waveform edits to allow that control, and then to bring the cohesion in with either room mics or parallel compression, and we'll briefly consider both. What tends to happen with room mics, as I say, this idea of it being a radical alter ego to the spot mics, is that it's the polar opposite with your processing approach with compression, which tends to be just simply bringing up the sound of the room, the way that the drum performance interacts with the room. And that involves fast attack, fast release compression. So it brings down the transient of the drums and then brings up the ambience. In some of your classic drum recordings, for example, when the levee breaks, which is often cited as the most emulated drum recording in the world, it was just based around room mics. So you might know the story about when they recorded When the Levee Breaks, and they brought the drums into the marble reception area and hung room mics up a spiral staircase above the drum recording. And then this idea of fast attack, fast release compression brings up the sound of the ambience, sometimes referred to as hyperventilating drum sounds. And you can listen to other examples, like more modern productions, like if you listen to Motley Crue, for example, there's a track called Till Death Do Us Part on the Motley Crue titled album, and you can hear those sort of like hyperventilating drum sounds there. But onto the subject of room mics. Typical approach then is fast attack, fast release compression. Let's have a listen to a room mic. This has been tracked without any printed compression whatsoever. And let's just have a listen to it as it stands. No EQ, no compression, either at the mix stage or indeed at the recording stage. Sounds like this. Applying an 1176 to that room mic, around 12 to 14 dB of gain reduction during peaks. Some producers will go a lot more aggressive than that and will often go up to sort of 20, 24 dB of gain reduction, but 12 to 14 dB of gain reduction during peaks sounds like this. And hopefully you will have heard there the way that the ambience of the recording is really brought up. The transients have been suppressed and the fast release brings up the ambience of the room. But also you might have listened to that and picked up on the fact that the cymbals have become quite abrasive as a result of this additional coloration and harmonic content. So what a lot of producers, engineers will do, myself included, is sort of frequency bracket the room mic to not only attenuate the abrasive highs that is resulting in these cymbals being a little bit on the obnoxious side, but also the low frequency content that can get a little bit on the muddy side. So what I've got here is a high pass filter around 120 and then a low pass filter gently rolling off the highs from around 2.5K, just reducing that cymbal abrasion. Sounds like this. And once I've got the room signal processed like this with this real emphasis of ambience, it just introduces a natural sense of cohesion to the drums, because with all these spot mics that have been waveform edited or gated, you can end up with disconnected components. They can sometimes almost sound like the separate components from a drum machine. And if you bring up this room mic, it just provides a sense of glue that glues all of the drums together in a more natural way, similar to a person stood in the room listening to the drummer. And that's in essence what a room mic is. It's almost representing being in the room from a distance away, where you're subject to the influence of the ambience of the room, which is very, very much less the case with the room mic. So let's listen to the drum sound without the room mic. Sounds like this. Now I'm going to introduce that processed room mic into that drum sound, but at a level where it doesn't mean that I lose the control that I've got. It's just a case of really finding a level where it introduces the cohesion, but without compromising that controlled drum sound that you've now hopefully now established. Sounds like this. And hopefully you will have heard that although it's relatively subtle, that it's glued the drums together. It just sounds a lot more cohesive and a lot more natural as a result. But of course, there are alternative approaches to cohesion that don't involve room mics. So to give you an example, Andrew Sheps does not like room mics, finding that they lack phase coherence, and Andrew Sheps's preferred approach is through parallel compression, which we'll consider now. So with standard applications of compression, the signal flow that usually makes sense is for the resulting signal to replace the uncompressed version. And due to the amplitude of the louder signal parts being reduced to be closer to the quieter parts, this can be thought of as downward compression. But with parallel compression, the technique of adding a compressed version to the original signal can be effective, and this is referred to as parallel compression, which can be considered as upwards compression. And in effect, what you're doing is using an aux sent duplicate of the relevant signals to an aux input track where compression is applied before being blended with the original versions at a level of our choice. And this application also involves downward compression, but usually with a very different approach. By forcefully attenuating the transient segments with heavy fast attack, fast release gain reduction, the quieter portions of the parallel signal are brought upwards. And obviously they're brought upwards when they're combined with the original tracks, which actually has the effect of dynamic control, but from a different manner than with standard downwards compression. In other words, the compression replacing the original signal, as is the case when you apply it directly to the relevant track or tracks. Importantly though, it doesn't have to be fast attack, fast release, parallel compression, longer attack settings can certainly be effective. And this is really an area where a lot of producers, again mentioning Andrew Sheps, is that Andrew will set up multiple different parallel compressors that bring different flavors, different coloration, and that have different characteristics, going back to that topology of those different compressors earlier on, and then just experiment with what they bring to the drum sound. So let's listen to the drum sound without parallel compression. Sounds like this. And I'll play that example one more time before jumping directly to the example with the parallel compression introduced. But here the parallel compression is provided by the distressor. Not entirely fast attack, it's more of a medium attack, but I've also got the Rev A, the UAD Rev A 1176 with my fast attack, fast release compression, and I've just blended those into the drum sound, but I've not done it too excessively because, as I've mentioned earlier, you can quickly lose that punch and control that you've already established by the time that you get round to introducing your parallel compression. So again, quick snippet without parallel compression. And then when you listen to the drum sound coming back in with parallel compression, just listen to the sustain of the snare drum with the flams at the beginning of the drum section, and you'll hear that the spit and the sustain of the drums has been brought up. Again, the example without parallel compression, and then into the example with parallel compression. And hopefully you will have been able to hear the additional harmonic content, that additional coloration, and the ambience and the sustain that comes when I've introduced those two parallel compression tracks to that drum sound. So although we only considered transient design with a snare drum, it's important to say that the principles are relevant with your kick and your toms or other instruments that you might be wanting to apply some transient design with compression to. But let's move on from compression to EQ, and from this perspective it would be wonderfully simple to think that if we could gain access to and employ the EQ settings used by, for example, Andrew Sheps, Chris Laudal, Jens Bogren, whoever it might be, that this would deliver the same results when applied to a different project. But in reality, it is highly unlikely this will be effective, as the EQ application on, that used by these producers was in response to a multitude of factors, which include, the specific shells, drum heads, dampening, tunings, the cymbals, the instruments, pickups, whatever instruments that they were applying EQ to. And importantly, the spectral content variation between different sounds on different multi-tracks can be absolutely immense, meaning that any presets or step-by-step instructions are really redundant. However, what I'm going to do is go through some broad principles that do come up on nearly every multi-track that I've dealt with has a tendency towards these principles. But of course, bear in mind what you're aiming for, what the blueprint of your own given project is, and then adapt any of these frequency moves accordingly for your own project. And the principle worth highlighting with kick, snare and toms is this idea of attenuating frequency components between the fundamental of the sound, the lowest frequency component of the sound, and then the brightness. And by attenuating those regions, whether it be the lower mids or the upper mids or some areas of brightness, it reveals the lows and highs. In simple terms, it's almost like you're looking at a smiley face on an EQ, and that the frequencies within the sort of middle ground of the sound, the lower or upper mids, or indeed the lower highs, attenuating them reveals the low end of the signal and also reveals the high end brightness. Sometimes with kick drums, producers refer to it as often being thud and click, certainly for indie rock and metal productions, but of course that might not be appropriate for your own production. You might be wanting a much more natural kick sound, in which case the extent to which you apply low-mid attenuation in this example with kick drums would be drastically reduced for that more natural sound. But certainly With the majority of kick drum sounds, I don't think I've ever heard a natural kick drum recording that hasn't required low-mid attenuation for an indie rock or metal mix. And it's just simply a case of sweeping around within the low-mid. So parametric EQ consists of three things. It's the ability to change the frequency, the ability to change the width of the Q, the bell curve, how wide that bell curve is, and then the ability to amplify or attenuate those frequencies. Semi-parametric EQ has the first and the last of those, but doesn't allow you to change the width of the Q. But from this perspective, you're looking at boosting significantly with a very tight Q and sweeping around the low mids to find out where the pocket of unwanted muddiness is, which is often between around 200 and 650. It depends on the kick tuning and the way that the kick size influences the sound of the drum and obviously the way it's performed. But you'll hear this muddiness content while sweeping around. And what I'll just do, I'll just play you a kick drum sound without any EQ. Sounds like this. By using sweep EQ and sweeping around the low mids of that kick sound, I've established that there's some resonant frequency content around 375. And with that frequency content boosted with a narrow Q and a significant boost, it sounds like this. So I'm now going to attenuate 375 quite aggressively, and I'm going to open up the Q relatively wide, as when I was sweeping around that frequency region of 375, the muddiness was over a relatively wide area. If it was over a narrow area, I'd use a narrower Q, but with the cut applied, it sounds like this. And that's just a corrective EQ move, but hopefully you'll be able to hear that the low frequency content and the highs are now sort of revealed with the kick drum. But I'm going to take it one step further and now apply boosts to the lows. This is down at about 85, and boosts to the brightness around 3.5K with quite a wide Q. Sounds like this. And now to provide a direct comparison between the kick without EQ and then with EQ. This is the kick without EQ. And now with EQ. And obviously the level of lows being boosted, highs being boosted, and low mids being attenuated would entirely depend on your own production and what you're trying to achieve with your kick sound. But that broad principle I could take further. I could look for, again, and it depends on the type of kick sound I was wanted, I could look for other regions within the low mids that were a little bit resonant. And likewise, I could look at if there's any content within the low frequencies that is a little bit muddy and attenuate that, and likewise any of the upper mid or high frequencies that are a little bit on the resonant side. So this broad principle that we've looked at with the kick drum, it will obviously be different for different drums, different tunings, different performers, but that fundamental principle we can apply to snare drums and toms. Let's take the same principle and apply it to snare drums. We'll listen to a snare drum without EQ, which in isolation might sound absolutely fine, but it's only when you get to listen to the attenuated resonant content again that reveals the lows and the highs that you'll hear the benefit of EQ. So this is firstly the snare without EQ, sounds like this. And then once we've attenuated that sort of honky resonant content, which there's some cuts around sort of like 530 and also at 385, and also a little bit of sort of like mids content at 1.1 that have been attenuated with the same principle of revealing the weight and the brightness of the snare, and with EQ sounds like this. And just a direct comparison without EQ to with EQ, the two flams without EQ, the two flams with EQ, sounds like this. Hopefully you'll hear the way that that's ringing, that sort of resonant content has made the snare a lot more powerful and a lot more controlled. And taking the same principle to toms now, Again, just looking for resonant frequencies in the low mids or upper mids and attenuating before then enhancing the weight and the brightness of the toms. Without EQ, sounds like this. Then with the corrective and creative EQ gestures introduced, the toms sound like this. And one more time, let's just go directly from without EQ to with EQ. Hopefully you'll be able to hear the improvement in the tom sound there, improved weight, less muddy, and with improved attack and brightness and improved tone to the toms overall. But again, those principles, it was just the same with the toms. I was just going through them, just looking for those low mid frequencies that just sounded resonant. By attenuating them, I'm revealing the lows and highs, and then I'm looking at boosting the lows and highs appropriately. And again, I know I do keep repeating this, but how you go about that needs to be appropriate to your production. And lastly, with EQ use for drums, let's briefly consider our overheads. And for me personally, the overheads on drums, whereas the microphones are facing down, the kick drum is projecting horizontally, so the overheads kind of capture that kick drum off axis. And for me, that sound tends to be quite unfocused. And so I will usually apply high pass filters to the cymbal mics at a minimum of about 180, 200, so just below usually where the fundamental of the snare drum is. However, for productions where I want more control, in other words, I'm turning the cymbals up and down and less turning the snare up and down, I can often go up to around 600, 650, so that the main body of the snare drum is quite heavily attenuated, and then you've got more control over the cymbals. And with that approach, let's just listen to the cymbals without EQ. And then with a high pass filter set at 550 on both those overhead cymbal mics, sounds like this. So with this high pass filter setting at 550, I was really looking for the most control of the cymbals so that when I turn them up and down, introduce them into the mix, it's less influencing the snare. But if I indeed wanted more of a contribution to the snare sound, as the snare captured in the overhead mics certainly will have a great contribution to a snare sound in a lot of productions, then I'd have the high pass filter a lot lower, maybe around 180, and that can often provide a more natural drum sound as a result. And on the subject of drums sounding natural, let's just briefly turn our attention to reverb use, which not only helps give the drums depth and dimension, but can also provide a more cohesive drum sound as you're going to send various drum components to the reverb that's obviously introduced in parallel on an aux channel. The reverb that you use needs to be very much tied to the speed of the performance, and perhaps stating the obvious, but the faster the performance, the shorter your reverb decays should be, and the less that you should be introducing reverb into that drum sound. The slower the drum performance, the more space you've got for these reverb decays to exist within, so they can be greater decays and usually greater influence of reverb. What I often like to do is sometimes set up 3 reverbs if you're not sure about the reverb processing approach with your drums. I can recommend setting up 3 separate reverbs, maybe a bright plate. For example, an EMT plate is a nice reverb for drums. Keeping it fairly short, maybe around 800 milliseconds to a second. And then a room reverb, like perhaps a large wood room from the LX480, which is a very lovely reverb for drums. Setting that around sort of like 1.5, 1.6. And then lastly, quite a long reverb, perhaps a hall reverb, perhaps around 2 to 2.5 seconds. And then experiment with the contribution from each of those. And again, if you've got a very fast drum performance, you would be looking towards the shorter side of the equation. And if you've got a really slow drum track with lots of space, you most likely want to be emphasizing those longer reverbs. So let's move on to bass guitar. I'm going to look at compression and EQ, but we're going to really reflect on the principles we've already discussed, which is this idea of dynamic stability, high threshold, high ratio, and then also looking at transient design. So in other words, if you had a bassist that had a lot of really transient content, let's say you're mixing the Chili Peppers, then firstly, well done you. Then you'll be dealing with slap bass performances. And although the old joke goes, what is the best processing approach for slap bass? And that's the mute button. Joking aside, you would need to consider whether you're wanting to smooth out that transient component of Flea's bass performance, or whether you want to potentially enhance that, or whether it's just signal stability, or is it just coloration. But the principles we discussed earlier with this idea of the attack setting, smoothing out the transient information, or helping enhance that and sort of balancing that attack, punch, decay, sustain relationship will be equally relevant to the bass. In any event though, the bass is unquestionably one of those instruments that different frets, different strings, different performance approach on those frets and strings can lead to greatly differing dynamics. And along with a vocal performance, the bass tends to be the instrument that needs a lot of compression for certain productions. Obviously, if it's more of a more spacious production, maybe it's just along with an acoustic guitar, you might want a more natural bass sound and you might not want that degree of dynamic stability. But for most bass sounds, a series bass compression approach is often favourable, which can involve perhaps compression on the channels as well as compression on the groups, maybe multiple compression on the groups. And again, with that compression being informed by, are you trying to smooth it out or make it more punchy? And again, with this central idea of dynamic stability, for it just to sit in the production so that bits of the bass performance aren't dipping in and out. And that's something that you should be listening to, is when you've got your bass processed, listen to it within the production at an appropriate level and make sure that all of the note velocities are contributing as they should do to the production. And dependent on the bass's role within that production, your EQ approach very much needs to consider, firstly, what are the guitars doing in the mix? This is a critical consideration. With a scooped guitar sound, in other words, heavily attenuated mids or low mids, there's often a spectral opening where you can sort of install the bass into the region where the guitars are attenuated, and this means they'll get on nicely. And the opposite is the case. If you've got guitars that are very mids heavy, then you can use a different approach with the bass where the low end of the bass is more emphasized, and that's going to sort of like sit below the mids content of the guitar performance, and they'd likely get on a lot better as a result, so not as likely to mask each other within the context of the mix. So let's have a listen to a bass sound without any compression and without any EQ. And the first thing you'll probably notice is the different notes and different strings have got quite varying velocities that mean that these bass notes are going to likely get lost within the context of the mix. So this is a bass sound without EQ and without compression. Hopefully you'll have heard that the higher notes on that bass performance part are not as clear and well defined and at a lower velocity than the lower notes, which gets corrected with effective compression use, as you'll hear on this next audio example, which also has some cuts around 870, just some honky sort of resonant content there. And there's also some attenuation applied down in the lower region around 230, and with the compression as well, that bass sounds like this. Then a direct comparison jumping from the bass without compression or EQ directly to having compression and EQ introduced sounds like this. Moving on to acoustic guitars. This is an instrument that, unlike the approach that we've used with bass, which is quite heavy EQ, quite heavy compression use, it tends to be an instrument that you need to treat a lot more gently. You just cannot treat an instrument such as the acoustic guitar, similar with piano, with aggressive gain reduction and aggressive EQ moves. It usually tends to be more about the amount of low frequency content and the amount of brightness within the sound so that it can deliver its intended role within the production. Let's just listen to an acoustic guitar without any EQ whatsoever. And then with EQ, which is mainly revolved around the brightness required for it to cut through the mix, and attenuated lows, the low frequencies within the context of the mix are just masked by the bass guitar. And by attenuating the lows, it further accentuates the high frequencies which are required for it to be present within the mix. And so with EQ, the acoustic guitars sound like this. And here the acoustic guitars were only compressed fairly gently with a VCA compressor because, as you remember, that's the cleanest topology of compressors. There's only about 3 to 4 dB of gain reduction with a 10 millisecond attack time. So let's stay with guitars, but let's move to the polar opposite of these clean acoustic guitars. Let's look at harmonically distorted electric guitars, and ones that are down-tuned at that. And due to the influence of harmonic distortion, which has this compression-like effect with electric guitars, they seldom need any further compression. You might want to add some compression for coloration, for example, but it's seldom the case that you'll need it for dynamic stability, unless of course there's quite a restricted application of distortion, in which case you might want to stabilize the dynamic content. But usually it's more about corrective EQ. With the majority of harmonically distorted guitars, there will be pockets of resonance within the guitars, and usually you'll find areas of abrasion within the guitar sound, unless they've been treated with printed EQ. That abrasion tends to be between 3 and 4.5 K, sweeping around that region with a significant boost and a tight Q. You'll find where the abrasion exists, and then you can attenuate it, broadening or tightening the Q according to how wide the range of abrasion is. And usually with harmonically distorted guitars, you will find regions within the low mids, sometimes as low as 180, 160, and that's an area where you can use either multi-band compression or dynamic EQ that sometimes guitar techniques such as palm muting. This is known as overly dynamic, frequency specific, but time variable. Similar to, for example, sibilance with vocals. We can't just attenuate that sibilance with static EQ because it would make the vocal sound darker when there isn't any sibilance in the vocal sound. So we use de-essing, which in effect is multi-band compression. Well, the same is often the case with electric guitars where, for example, again with palm muting, you get this excessive dynamic content in a frequency region, but only when the technique's getting used. So if we apply, for example, dynamic EQ or multi-band compression, it will attenuate these problematic frequencies when they come up, but hopefully without impacting the signal the rest of the time. So let's listen to a couple of audio examples. Firstly, with rhythm guitars without any EQ, sounds like this. You'll hear that there are some abrasive qualities in this guitar sound, and it is a little bit muddy in the low mids. So after attenuating the low mud range, attenuating the abrasion, this has revealed the low frequencies and the high frequencies, but the guitar's signal still has been brightened up somewhat. And so here you're often negotiating between the brightness you require, and that brightness will sometimes introduce more abrasion. So you're sort of like negotiating between the additive moves for brightness and the corrective moves to attenuate the abrasion. And with those EQ gestures introduced, the guitars sound like this. And to more clearly reveal the before and after processing, let's go back to the guitars without EQ and then straight to the guitars with EQ. And hopefully there you will hear the way that the low-mid attenuation has revealed the lows, and likewise that the attenuation of brightness has helped reveal the more pleasing brightness slightly further up the spectrum, around sort of 5K, that's been further emphasised with a boost. All right, let's last but very much not least, let's move on to vocals. As you remember from last month's Sound on Sound recording and mixing podcast on vocal recording, vocals are the most dynamic instrument in the world, going from a whisper to a scream within a millisecond, and controlling those dynamics can be really challenging, particularly in a more dense mix. So the denser that the mix is, particularly when it's harmonically distorted electric guitars or where it's multiple instruments, maybe you've got strings, brass sections, keyboards, the denser the mix, the more likely it is that you will lose certain parts of the vocal performance within the production because they're just not intelligible enough. And obviously a much more dynamically stable vocal will stay present to the listener. And it's all about delivering the intentions of the performer, the intentions of the vocalist, delivering that to the listener. And if there's certain parts, you know, maybe the quieter, breathy parts of the vocal are not clear to the listener, you've not represented the vocalist. So let's listen to a vocal that, although there's some effects processing, a little bit of reverb and delay on there, it hasn't got any EQ and hasn't got any compression applied. Sounds like this. A chrysalis in serpent skin, an echo of a requiem. And then with quite an aggressive series compression approach. So to be clear here, I've actually combined 3 different compressors, each delivering several dB of gain reduction during peaks. So I've gone for a FET compressor, very fast attack, fast release, delivering 7 to 8 dB of gain reduction, a VCA compressor, delivering the same amount of gain reduction but with a slower attack time of 3 milliseconds. And then lastly, an optical compressor, which is an LA2A grey revision from Universal Audio. And that's delivering several dB of gain reduction as well. But each of those compressors, due to the different ballistics, the different attack and release settings, are each grabbing and releasing the signal at different times. And the analogy here is, it's like, instead of having one big thick layer of varnish that doesn't dry in a smooth way, it's got a lumpy finish. If you were to apply 3 layers of varnish, finer layers of varnish, it's less likely to be lumpy and it's going to be a lot more transparent. So again, there's in excess of 20 dB of gain reduction applied to this vocal. And at the same time, once I've applied this compression and listened to the signal, there's a little bit of abrasion come out in the vocal. And this was around 8.6K and slightly lower at 3.7K. And I've attenuated those little pockets of abrasion, which again reveals more pleasing brightness, which I've further enhanced with a boost with a sort of Baxendall curve, which continues to rise rather than a shelf, rising up into those upper high frequencies around 10 to 12K, where it's often referred to as air frequencies. Let's have a listen. A chrysalis in serpent skin, an echo of a And just to allow you to hear those differences a little bit more clearly, let's go straight from the vocal unprocessed directly to the vocal with compression and EQ.
A chrysalis inside my skin. A chrysalis inside my skin.
And at the same time as the vocal being more dynamically stable and with a more pleasing tone, hopefully you will have heard the way that the vocal has been impacted by coloration from those three different compressors, the optical, the VCA and the FET compression. Despite this coloration though, perhaps the most important element of a vocal from a frequency perspective is its brightness within the mix, and particularly alongside the electric guitars. If the vocal is a lot brighter than your electric guitars, which operate in a similar frequency spectrum, it just won't sit in the mix properly no matter what the mix level. And if it's too dull, it will appear to be behind the guitars from a proximity perspective. And again, you will really struggle to find a mix level for the vocal. So it's a case of just listening and trying to get a similar level of brightness from the vocal and from the guitars. And just to wrap up this podcast, let's briefly discuss vocal processing as far as effects go. Generally speaking, the 101 of vocals is to use reverb and delay lines. And again, I can recommend adopting this approach where you experiment with different decay times and different types of reverb. Same with the drums, we looked at using a plate reverb and a room and a longer haul. And again, the speed of the vocal performance, is it very long held notes, which would suggest you could use longer reverb times? Or is it a faster rap vocal, which would mean you'd go towards shorter decay times and likewise less influence of reverb? And then when we're looking at delay lines, the first thing you need to do is look at musically appropriate rhythm settings from the delays. So sometimes this will be an eighth note each side, sometimes it will be slower with quarter notes. Easiest way to do this is listen to end of lines. Hit your space bar to stop the vocal and just listen to the rhythm repeats from your delay lines. You might want to experiment with different delay lines in left and right, so perhaps with a dotted note, a slightly longer delay in one of your speakers, or alternatively a triplet, which will quicken up the delay time. And again, just listening to multiple delay lines potentially interacting simultaneously, just making sure it doesn't clutter the rhythm structure of the vocal. Additionally, or alternatively, you might want to consider slap delay, which is usually around 150 milliseconds without any feedback settings. So just a single slapback repeat, which was used extensively in the early sort of 60s records. Elvis Presley, for example, always had slapback echo on his vocals. And again, experimenting between different delay lines and just blending those along with different reverb characteristics can be a favourable approach. Then at the same time, if you want to push it a little bit further, you can use stereo widening techniques. And there's some great stereo widening plugins out there. For example, the S1 Imager by Waves is really great with vocals, and that can just lead to a lead vocal being less monophonic. So in closing, thank you very much for listening to this Sound on Sound recording and mixing podcast focused on mixing. And if you haven't done so already, do take opportunity to check out the earlier podcasts on recording drums, bass, guitars, then vocals. All the best to you. Bye-bye.
Thank you for listening, and be sure to check out the show notes page for this episode, where you'll find further information along with web links and details of all the other episodes. Oh, and just before you go, let me point you to the soundonsound.com/podcasts website page, where you can explore what's playing on our other channels.